Okay, this video is going to be about moment of inertia, but now in 3D. In 2D, moment of inertia was essentially a scalar for all practical purposes. At least we used moment of inertia as a single scalar quantity, Ig. In 3D, however, moment of inertia is a tensor in general, and then if you want to represent the tensor, you can represent it as a 3 by 3 matrix. Okay, so what is moment of inertia? Just to recap, it's the rotational analog of mass. Moment of inertia includes mass, but also the distribution of mass around a particular point. So in that sense, it's not as fundamental as mass. Mass is sort of a fundamental physical quantity. Moment of inertia is a derived quantity that takes into account the mass distribution around a point. Okay, you can think of moment of inertia as just a way of simplifying the expression for angular momentum of a rigid body. So we will get to that in the next few minutes. So, in a sense, moment of inertia is just a mathematical convenience that people invented, a quantity that people invented that captures the distribution of mass in a manner that you can write the expressions for angular momentum or the rate of change of angular momentum, even of a rigid body in a convenient, simple manner and in a short form. Okay, let's look at it. Look at how this is so. First, let's recall what angular momentum for a point particle is, right? So imagine there's a point particle P with mass m and velocity Vp going this way, okay? And this velocity Vp, when we say velocities, usually in this course, it's always with respect to some reference frame that is inertial. It's an inertial reference frame, okay? So that's the mass m. This is the velocity of the point P. The angular momentum of point P about some other point Q is defined as follows. This is just a definition. It's the linear momentum, m times Vp. And then you take the moment of the linear momentum about the point Q. So it's Rp with respect to Q cross, this is a cross product, mvp, right? So that's a cross product. Okay, so that's angular momentum of a single mass point about some other point, okay, R cross mvp. Now, what is the generalization of this to 3D? It's just a direct generalization. No new ideas are being introduced here. So imagine you have a 3D rigid body, and you have a small element in the 3D rigid body, which has mass dm. It's a differential element with some small volume, and its mass is dm or delta m. And the center of mass is point G, which is not necessarily at this point. It's somewhere, right? So this is just a general differential element. Okay, consider a general rigid body with a center of mass G. Then you can consider the angular momentum of just this differential element. The idea is that once we write down an expression for this differential element, we can do the angular momentum for the whole rigid body by integrating over the whole volume, okay? So for just that little differential element of mass dm, the angular momentum is exactly the same as this expression, except we've replaced m with dm, okay? So it's exactly the same expression, rp with respect to g cross dm vp with respect to g. And that's because we are now writing the angular momentum about point G. So we are writing Vp with respect to G here, okay? It is the angular momentum about the point G. So what do we have here? We can simplify that a little bit here. Vp with respect to G, what is that? If P and G are 2 points on a rigid body, if you have P 2 points on a rigid body, then we know that Vp with respect to G can be written as omega cross Rp with respect to G, right? So this because Vp with respect to g equals omega cross Rp with respect to g. Okay? And that's true if P and G are 2 points on a rigid body. Okay. So we have this expression now. What is this expression? Well, this is just the expression for a differential element, for angular momentum of a differential element at point P. Okay, the angular momentum for the whole rigid body is now the integral of this little angular momentum over the whole rigid body. So h underscore, or with respect to g, is just integral of this quantity. Okay, and the integral is over all mass, and we are integrating over all the differential elements within the mass. Or another way of thinking about it is that it's a volume integral. Essentially, it's a triple integral or volume integral, integrating over the whole volume. Okay, so we'll get to that later. Okay, so this is the expression for angular momentum in 3D. Now, can we simplify this further? Let's do a 2D special case first, how to think about this sort of messy looking expression superficially in 2D. Okay, special case 2D. Let's basically write this equation down and then sort of expand this out for the 2D case. Let's say some point P is represented, this differential element point P is represented by xb and yb in the coordinate frame exb eyb, where this frame rotates with the body. It's a body fixed frame. So in other words, as the body rotates, this frame also rotates exactly with the body, rigidly attached to the body and rigidly attached with origin at G. Okay, not that that's super important here. Okay, so that's Rp with respect to G. We just defined the coordinates of any point P. Omega, because it's a 2D problem, is just perpendicular to the plane. So it's perpendicular to the plane and it's only along EZ. And you can call that E sub EZ B if you want, because all the Z axes are going to be the same for our purposes here. Okay, so this is the expression for the position of the point. This is the expression for omega. Now let's compute this cross product, which was key here. We just plug these things in and then expand it out. And what we get is omega times xb square y sub b square ez. Okay, this is the angular momentum. Well, this is not quite the angular momentum, but this is a big component of the angular momentum. Let's take this now expression for this cross product and plug it into this expression, and we get the angular momentum in 2D is integral. That whole cross product comes down here, omega xb square plus yb square. The dm sort of comes down as well. We are integrating over all the masses in the rigid body, on all the little pieces of mass in the rigid body, and the angular momentum is only in the EZ direction because we are still in 2D, and we can rearrange things. Omega itself is just a single quantity that is applicable for the whole rigid body. Omega cannot depend on the position of the point that you're considering. So omega is a property of the whole rigid body. So that can come out of the integral. And then xb and yb are, well, that essentially represent the various points on the rigid body. So Ez is just a constant vector as well. So this quantity becomes this integral times omega z. And this integral xb square plus yb square dm, integrated over all the mass in the rigid body, is what we call moment of inertia about point B. Okay, this quantity is what we call the moment of inertia, right? It's, if you call this is xb, this is yb, This is RB or something like that. Basically, this quantity is also integral RB square dm, and that's equal to IG. Okay, so it's integrating mass times how far the mass is from the point G squared, integrated over all the mass, right? So basically summing over all the masses, mr square essentially. That's basically IG in 2D. Okay, so that's a 2D problem, and that's what we've been using so far. We've not explicitly done this derivation, but implicitly all the IGs we've been using have been derived using this formula. Okay, so for instance, if you had a thin ring, you can show that Ig equals mr squared because every piece of the mass is at a distance r from G. If you have a uniform disk, then you can show now using a double integral that the moment of inertia Ig, the 2D moment of inertia Ig, is mr squared divided by 2. I'll let you guys think through this derivation. If you have a uniform bar, it's ml squared divided by 12 about G. If you have a uniform rectangle of length L1 and L2, then Ig is ml1 squared plus L2 squared divided by 12. Okay, those are all some simple examples. If you want a longer list of standard objects with their moments of inertia, you can look up an online list or lists in various standard textbooks. Now, what about the 3D moment of inertia? In 3D, it turns out the moment of inertia, the object moment of inertia is either a matrix if you want to think about representation in a frame, or it's a tensor if you want to think of it sort of representation free. Okay, so it's basically a two tensor or matrix. For the purposes of this class, you can just think of it as a 3x3 matrix. Okay, so why is that, or how is that? Well, that's the next derivation. We now consider now a 3D rigid body. We have a body fixed frame here. It doesn't actually have to be a body fixed frame. The following derivation doesn't depend on this being a body fixed frame. So it's just some frame B, but we'll see that if it's a body fixed frame, things become simpler. It's just some frame B, and then we have some differential element, dm, with coordinates xb, yb, zb in that frame. Okay, so, and then we write omega, the angular velocity of the rigid body, also in the frame B, omega xb, omega yb, omega zb. Rp with respect to G is this quantity as we just noted. And then we can write this cross product out for the sort of differential angular momentum quantity, or the angular momentum of the differential mass element. Okay, so we just take this and plug in these expressions for omega and Rp with respect to G and evaluate this cross product. There are sort of simpler, more abstract ways of doing this calculation, but I thought I would keep it elementary and just do the cross product in long form. You just take this cross product, do a couple of cross products, and you get these expressions. We first notice that these expressions, well, first of all, we are writing this vector in the coordinate frame exb, eyb, ezb. Okay, and the second thing we want you to notice is that this expression is linear in omega xb, omega yb, omega zb. Okay, so because it's linear in omega xb, omega yb, omega zb, we can write it in sort of a matrix form, matrix of coefficients times omega xb, omega yb, omega zb times dm. That's the representation of this vector in frame B. Okay, representation of this vector in frame B. I've dropped the exb, eyb, ezb and just decided to write it as a matrix. Okay. Of course, this is the differential elements angular momentum, and we can integrate over the whole body to get the angular momentum of the whole body. So what we have is basically an expression where angular momentum of the whole body is basically the integral of this thing times this thing, right? The integral of this matrix times dm is what we are calling ig, and then omega is omega, just comes from there. This is the representation of omega in the frame B, and this integral of this matrix is the representation of the moment of inertia tensor in the frame B. It's going to be a 3 by 3 matrix. Okay, so we're going to call this matrix the moment of inertia matrix in this frame, which is going to denote it ixx, iyy, etc. Right? So standard notation for a matrix where each of these quantities is an integral. This is an integral, this is an integral, and so on. And what that integral is comes from this expression. So for instance, ixx is integral over the whole body of yb square plus zb square. This should have been zb square. Iyy is there are some typos here which I'm fixing on the fly. Iyy is basically zb square plus xb square. Izz is correct, xb square plus yb square, right? So if it's xx, it's the other two coordinates. If it's yy, it's the other two coordinates. If it's zz, it's the other two coordinates, x and y. Okay, and the other thing is that instead of integrating over the mass elements, we can integrate over volume elements. So you can replace a differential element of mass into replace mass of the differential element by a density times volume dv of the differential element, and the density can potentially be constant or depend on x, y, z as well. So this can be a variable. If it's a constant, you take it outside. If it's a variable, you substitute whatever function of x, y, and z it is in while doing this integral. In any case, these integrals are essentially volume integrals. Notice that there are these cross moments of inertia, x, y, and yx, and they both have essentially the same expression, integral minus xb yb times rho dv or dm. Of course, because xb yb is the same as yb xb, ixy is the same as iyx. Same for these things. Okay, because of this property, which is commutativity of just simple multiplication, the moment of inertia matrix is going to be always a symmetric matrix. Okay, symmetric matrix. Sometimes people use the notation that ixx and ixy or iyx is actually plus. Instead of this minus, plus. Instead of this minus, they put a plus here, and instead of this minus, they put a plus here. That is a convention sometimes that is used, and if you use that convention instead with the plus here for the definition of these quantities, then the moment of inertia tensor or matrix itself will have a minus for the off diagonal elements. So that's just an alternate convention that some books or people use. I tend to use this notation where the matrix itself, the elements of the matrix itself is just doesn't have any negative signs, and then we have a negative sign in the off diagonal elements definition. Okay, so that's the matrix, elements of the matrix, these elements are the elements as this tensor, moment of inertia tensor, is represented in frame B. Okay, So Ig is called the moment of inertia tensor. It is essentially a linear transformation that operates on angular velocity, right? So what is it doing, right? So it's operating on angular velocity to give angular momentum, right? So this is a linear transformation that takes in one vector and gives another vector. In this case, they are matrices, 3 by 1 matrix, 3 by 3 matrix, 3 by 1 matrix, as represented in frame B. But more generally, it takes in one vector, omega, and gives you another vector, h, with respect to B, angular momentum with respect to B. Okay, so that's the moment of inertia tensor. This is what it does. So written in sort of abstract form, it takes in a vector, operates on that vector, and gives you another vector. That's why it's called a tensor, because it's the linear transformation from one vector to another vector. Of course, like I just said, the above expressions that we wrote down, these integrals, are the representation of the Ig tensor in frame B. And that tensor, that 3 by 3 matrix, takes a representation of omega in frame B and gives the representation of Hg in frame B, right? So this is what it does. This is a 3 by 1 matrix, 3 by 3 matrix, 3 by 1 matrix. Eventually, we'll just be dealing with representations, so that's fine. This is pretty much all we need to think about. Okay, note number 3, let's say we have the moment of inertia matrix in some frame B, and then we want its representation in some other frame S. How do we get that? That's pretty straightforward. We can just take this expression and then sort of transform this expression to frame S by saying Hg in frame B is basically rotation matrix R S to B, Hg in frame S. Do the same for omega, and then bring this down here because R is a rotation matrix. This becomes R transpose, and essentially we have the new relationship Hg in some other frame S equals this quantity times omega in some other frame S, and this quantity is basically your Ig in this frame S. Okay, so if you want to transform the moment of inertia matrix from frame B to frame S, this is how you do it. You pre-multiply and post-multiply. You post-multiply by the rotation matrix, pre-multiply by the rotation matrix transpose. It's basically a similarity transformation, if you're familiar with that, except because the inverse of a rotation matrix is a transpose, you just do a transpose, okay? And then that's officially note 3, and then note 4 is that, well, we already talked about this, moment of inertia matrix is symmetric in any frame B. When you say in any frame, you don't really have to say B. And then note 5. Now is actually the first time we use the fact that B might be a body fixed frame. So far, everything that we have said, B need not be a body fixed frame. But if B is a body fixed frame, what do we mean by that? It means that as the body moves, the frame B also moves. Frame B is rigidly attached to the rigid body. In other words, it doesn't move relative to the rigid body at all. If B is a body fixed frame, defined in that manner, then it turns out that the moment of inertia matrix in that body fixed frame B is a constant. Like each element will be a constant because the frame doesn't move relative to the body, so all these integrals will just result in some constants because the points are not moving relative to the frame B. Okay, so if B is a body fixed frame, then I in frame B is a constant. In any other frame, if you have the body moving relative to a frame, the moment of inertia of the body relative to that represented in that frame will change. Okay. So that's an important point because moment of inertia as a constant in the body fixed frame, it's most convenient to express moment of inertia matrices in the body fixed frame. So we will do that a lot. Okay. Here are some moments of inertia matrices in body fixed frame, sort of given here. So here's a solid sphere. Solid sphere. It's a diagonal matrix with these on the diagonal, right? So of course, I hope it's obvious that when we say M and R here, it's the mass of the sphere M and radius of the sphere R. Okay, and then if you have a thin spherical shell, it's a different diagonal matrix. If you have a cuboid with these as if these as the axes of the body fixed frame, then and then L, B, and H as the length dimensions, then these are the it's a diagonal matrix again with diagonals being like this. If you have a thin rod, it turns out it's just sort of a special case of a cuboid. When we say thin, we mean thickness basically 0. And like we said, it's a special case of this guy with H and B equal to 0. Okay, so that's how you get this expression. Okay, so that's the thin rod, and then uniform disk. We already saw the 2D disk. For 2D disk, this is the moment of inertia. Moment of inertia about the z-axis is actually mr squared by 2, and about each of these axes, it's going to be mr squared by 4. If you had a ring, then it's going to be mr squared about the z-axis, and then izz is going to be mr squared, and then these two are going to be mr squared divided by 2. So this is what we derived earlier, and then it turns out these two add up to this thing. For a planar object, it turns out if z is the perpendicular to the plane, then ixx plus iyy equals izz, but only for a planar object. That's sometimes called the perpendicular axis theorem. In any case, these are just some simple examples of standard objects with their 3D moment of inertia matrices. You can look at tables, say, on Wikipedia or other textbooks for moments of inertia matrix for other standard objects. Also, various geometric modeling softwares like SolidWorks will have ways, once you define the geometry and the density properties of an object, have ways of computing moment of inertia matrices given geometry and density. Okay, so let's stop this video right there and talk about one small aspect of moment of inertia matrices in the next video.